For multiple assets, it's a little bit more complicated, so there is no nice formula for that if you have, say, 100 assets. There is a nice way using matrix algebra, but as I mentioned, I don't want to torture you with that. But there are formulas that you can look up in basically all textbooks that give you the minimum variance portfolio solution for like 100 assets if you like. Right? It's, not something that you have to manually do yourself. There are solutions for that already, so just use them. And typically, what you can see here is that the correlation coefficient is here at 2 instances up there and there. And typically, the minimum variance portfolio has a positive weight in both assets. But for very, very large positive correlations, it might be 100% in one asset. Right? Okay, so if you look at the case here for the sigma equal to 0.5, the minimum variance portfolio is asset A, right? So there's 0% of asset B in there. But this could potentially give you negative results or results larger than 100% if you allow for short selling, right? So this formula works perfectly if you incorporate short selling. So any questions? So then let's extend this a little bit, or let me just show you basically without formulas what the result is for many risky assets. And that looks like this. So now we have several assets that we can number. So maybe we have asset 1 here, 2, 3, 4, 5, and 6. Basically, so in my slides, this is a gray shaded area. Not quite sure why it's not shown here. So basically, all the stocks or assets that you have are in this area here. Right? You can have as many of them as you like. Now, if you combine them, you will get portfolios which are within this shape here. Right? Depending if you mix 1 and 2, just learned it's a hyperbola between 1 and 2. Right? If you mix 4 and 5, it's a hyperbola between 4 and 5. Right? So all the combinations of those assets will be in this total area. You can never be outside the area. So if you look in the slides, in the white area you can never end up with, but you can end up at any point in the gray shaded area. Right? So all feasible portfolios are in this area. You can never end up outside the red curve. You cannot never be here, you can never be here. Right? So that's all impossible. Right? So the portfolio weights now will be kind of, we'll have multiple, right? So this will be W1, W2, W3, W4, W5, and then you would have here, this will be your W6, but that is basically 1 minus the other W's. And again, we have our minimum variance portfolio that we can plug in here. So that's the minimum variance portfolio. All right, so the important finding here is that the hyperbola shape is still kind of obtained. They're not just on the border here, they're not on the red curve, but they're within the area surrounded by the hyperbola. So one note here, that's of course still excluding the risk-free asset here. But as I mentioned, the logic from our first example can be applied to anything, right? So for example, if you want to combine the minimum variance portfolio with the risk-free asset, it will be a straight line through those points, right? You have your risk-free asset, say here, and your minimum variance portfolio here, it's a straight line through these 2 points, right? So that finding does not change when you use portfolios instead of individual assets. now we have kind of a big set of alternatives. We know that all our choices that we can obtain are in here. We can't get anything here, unfortunately, but we can get everything in here. So the question is, which of those portfolios are attractive, generally speaking? And for that, we actually need to make some assumptions. So these are now the assumptions put forward by this guy called Harry Markowitz, and he started this in 1952. And the capital asset pricing model, I think, was developed in early 70s. It took some time kind of until the extension happened. And for me, this is actually something, maybe just to highlight this, is really important for me, that you are able to separate what the assumptions are and the results of the theory. Might seem like an easy thing, but if I read a thesis, for example, or seminar papers, I often find that people confuse that. Maybe I've already mentioned that the return of an asset should be linked to the beta, right? So you want to see. So some people tell me or write in the thesis, well, Harry Markowitz or the theory assumes that the beta is linked to the return. Well, is it technically an assumption? Actually not, it's the result, right? So people use the word the theory states or assumes when they're actually describing a result of the theory. And this is something everyone has kind of their kind of oddities and things that they look for, like a button you should not push, and this is kind of my thing. I'm pretty transparent about it. So for me, it's really important to consider the starting point of the theory and the end point. Right? So the theory starts with a set of assumptions, and then you do some logical operations, hopefully logical, and you end up with a couple of results. So for the important theories that we discussed here, you should be able to name what the assumptions are and what the results are. And to separate those, kind of what's the consequence of something, right? So the assumptions are the starting point, right? We're just basically, they're not truth in that sense, we're just assuming they're truth. And the results follow from the assumptions, right? So the logical consequence. Now, the empiricists would do this in the reverse. They would basically look at, okay, we have a result, a prediction by the theory. Do we find that in the data? Right? If we don't find it, well, what's the consequence? The consequence is that some of the assumptions must be badly chosen. Right? So the empiricists work in the opposite direction. They check the results, and then they say, okay, we have to falsify the theory in the sense that the assumptions may not be well chosen. So there must be kind of some loophole. So every person that you will probably interact with here that are candidates for thesis advisors will have some things that they look carefully at. My PhD advisor was always kind of giving like a 10-minute rant if someone was mispronouncing a name of a researcher. So there's a formula about Black and Scholes, and some people say Scholes instead of Scholes. And Scholes is a football player from Scotland, I think. So I've heard that rant, I think, 20 times because I've sat in so many seminars with him. And so that was kind of his thing, and this is my thing. Like, do not confuse assumptions and results. It's something that annoys me a lot. And I take care that I write down assumptions and results separately in my slides. So it should be apparent, like, what is a result and what is an assumption. So try to separate that as good as I can. Good. So what are the assumptions here? So the starting point are these three things. So the first is that we are in this perfect frictionless market environment. That means we're ignoring transaction costs, we're ignoring taxation, right? Which is quite important because you have to pay taxes on the results of on the income you have from your risky securities, right? On your returns. And if there are differences in tax treatments, that might have an impact on your decision, but we ignore that for the time being. We have investors which are characterized by two things. The first thing is that investors only care about mu and sigma. Right? So the sigma is the correct risk measure for that individual. That's how they perceive risk. Right? So basically, they are living in this world where they can put everything in this picture here, and they're happy with that. Right? There's no information outside this picture that investors are considering. Right? Again, probably in real life, there is things that are things that are important and they should consider, but in this theory, there isn't. And finally, we need to assume risk aversion. Right? We discussed risk preferences before, so All of these theories that you will study here only work with risk aversion.